Hello and welcome to this 7th lecture for our course on blockchain and its applications. And this is the 5th and last lecture in the topic of basic cryptographic primitives. So, today the concepts that we will cover, it includes RSA encryption and decryption. So, if you remember from our last lecture, we discussed about what is cryptography. We have also discussed what is symmetric key cryptography, public key cryptography, and then we said that RSA is one form of public key cryptography. We have seen what is the basic concept behind RSA. So, today we will see a little bit more about how encryption and decryption can be done using RSA. Then we will move on to discussions on digital signature, which is what we have been talking about for some time. So, the two main components of cryptography that are having a lot of applications in the context of blockchain are, one, as we said, is the cryptographic hash functions, the other is digital signature. So, after we understand how RSA encryption and decryption works, we will move on to our discussion on digital signature. And then we will see that hashing and digital signature, how they are combined and they are used also in the context of blockchain. So, these are the basic concepts that we will cover, and the keywords for today's lecture are of course RSA and digital signature. So, let us continue our discussion on RSA encryption and decryption. If you remember that we said that there is a message M which is called the plain text, and then we use RSA for encryption using the encryption key, and that will generate what is called a ciphertext. And once the ciphertext is generated, it can be sent from one user to another user, and then the recipient can use the decryption key on the ciphertext to get back the plain text. So, that is the idea behind public key cryptography and of course, also for RSA, as we have seen. Now, how is encryption done with the public key? So, the public key actually, if you remember that we generated this n in the last lecture, how to generate n, we said how to choose two large prime numbers and from there how to get n, and then this encryption that is done, it is done with the public key. And if I denote the public key as this tuple, which is the encryption key part of it, which is E, and then the n, which is how we discussed about this encryption steps in the last lecture as well. Now, if we are given say a particular message capital M, what we do is that we first have its integer representation, say let us call that as lowercase m or small m. So, what we do is that in the process of encryption, we raise m to the power of e, and then whatever we get, we take the remainder by dividing by n. So, that is what is m raised to the power e mod n, and what we get as a result of this operation, that is what we denote as the encryption process, and C is a representation for the ciphertext. Okay. So, this ciphertext is obtained from the plain text M. So, capital M is the original plain text, its integer representation is lowercase m, and then from there by applying this operation with the encryption key, which is the public key, we have got the ciphertext C. Now, if this C is transferred from one user to another user, now what will the recipient do? The recipient will decrypt it using the private key. So, it also implies, as you have understood from our previous discussions, is that if Alice is sending a message to Bob after encryption so that nobody else can see it, then Alice will be using which public key? Alice will be using not her public key, but the public key of Bob. So, this E that we talked about in the step of encryption with public key, so that E and N combination, that is the public key of Bob, who is the intended recipient of this message. And now Bob will be using the private key, which is this tuple d comma n, and only Bob is supposed to know this private key, and hence only Bob will be able to decrypt the message. And how Bob does the decryption? So, Bob has received only C from Alice, right. So, because the public key is known and the message was encrypted and the ciphertext was derived, which has been sent out to Bob. After receiving the ciphertext, what Bob will do is that Bob will now apply this step, which is raising that ciphertext C to the power of D, which is the part of the private key, and then take modulus n operation on that, and whatever remainder Bob gets, that is supposed to match with the original plain text, which is m. So, that means that C raised to the power d mod n, but C, what we see in the previous bulleted point is that C is m raised to the power e of mod n, and then this m raised to the power e of mod n, then whole raised to the power of d. So, that will be m raised to the power e raised to the power of d and mod n, and this modular arithmetic can be shown that this m raised to the power e raised to the power d mod n and whole mod n is same as m raised to the power e raised to the power of d mod n, and that will give us back the value lowercase m, and that integer representation again can be converted back to the actual message m. So, finally, through this process what has happened is that Alice has been able to send a message securely to Bob, so that any adversary who might be able to catch hold of this ciphertext C in between also will not be able to get back m, because the private key d n is not known to the adversary. And this is what we are talking about of an application of RSA, where the goal is that no adversary in between can read the message. So, that is what we have to keep in mind. We take an example, and this example has been taken from the book by Stallings on cryptography and network security. Let us consider these two prime numbers. If you remember, we said there are two prime numbers to be chosen, p and q. So, let us choose p equal to 17 and q equal to 11. Of course, the actual p and q values will be very, very large. And then we calculate n equal to p into q, which is 17 into 11 and is equal to 187. And then we compute the Euler's torsion function, that phi n, which for these prime numbers p and q can be shown to be equal to p minus 1 into q minus 1, which is 16 into 10, and that is 160. And now we have to select an E is the encryption part of the key, such that E is relatively prime to phi n, which is 160, and also less than phi n. And we can choose many possible values depending on what is the value of phi n. So, in this example, let us choose E equal to 7, because E equal to 7 will satisfy the requirements that are mentioned in this bullet. And then we have to choose a value of d such that d into E mod 160 will be equal to 1, and d will be also less than 160. Okay. So, we can determine that d is equal to 23, because we see that 23 into 7 equal to 160, 161, and 161 is 1 mod 160. So, if I divide 161 by 160, I get 1 as the remainder. So, that satisfies the condition that d into E mod 160 should be equal to 1. So, in this way what we have got? We have got the encryption key, we have also got the decryption key. And if you remember this E and N, so in this particular example, this 7 and N is equal to 187. So, they form the public key, and D comma N, that is 23 comma 187, that forms the private key. Now, how is this encryption of plain text M is done? So, let us consider the integer representation of the plain text is say 88. So, what we will do is that we will get the ciphertext, which would be 88 raised to the power of 7 mod 187. Why 7? Because 7 is the encryption key. So, 88 raised to the power 7 mod 187. Now, we can do a little bit of this jugglery where we slightly arrange this modulus so that we do not have to raise 88 to a very large value and then try to apply a mod on that. So, instead what we do is that we can simply use a little bit of this modular arithmetic, and this 7 we break it up into this 7 and this 2 and this 1, as you can see, and then we can also break it up this mod 187 on each of them individually, and then the whole mod 187 that stays. So, this mod 187 stays here, as you can see. And then each of these, if we compute, which is much easier to compute as compared to raising 88 to the power of 7 and then doing mod 187. So, individually we raise it only to these powers of 4, 2 and 1, and then we get 88 from here. You can easily compute that, and then 132, and then you multiply these 3 and then you divide it by 187, and you will see that the remainder that you will get is C. So, this is 11, which is C. Now, this 11 has been sent to Bob by Alice, and then what Bob will do is that Bob will follow the steps that we had mentioned in the previous slide, and Bob will also now raise 11 to the power of not 7, but 23, which is the decryption key, which is part of the decryption key along with n, which is 187. So, what Bob does not know what is the original plain text. Bob has only got the cipher text, which is 11. So, Bob is raising 11 to the power of 23 and then applying mod 187 there, and again we can do a little bit of these adjustments. This 23 we break it up into this 1, 2, 4, 8 and 8, and then we get this simplified form by which we can get this from each of these parts of this equation, and then we get finally this 797202245 mod 187, and if you compute it, you will find that we end up getting 88, which indeed was the original plain text that was encrypted by the encryption key, that is the public key. So, in effect what we have seen is that Bob has been able to get back 88. So, Bob had this C as input, Bob applied these operations and gets back something which by the property of this public key private key pair of RSA should exactly be the same as the original plain text 88. So, that is how this RSA encryption and decryption works. Through an example we have shown it. Also remember, as we had mentioned before, that if this plain text 88 was encrypted by this 23 and 187, this combination, then whatever we would have got as a cipher text, and then if we applied the decryption process on that cipher text using this key of 7 and 187, this pair, we also would have gone back the result. So, that means that for any plain text M, if we first apply the public key and on top of it we apply the private key, we will get back the plain text. Similarly, on the same plain text, if we first apply the private key and then on top of that we apply the public key, we will get back also the plain text. So, that is an important property of this type of encryption and decryption using RSA especially. So, that tells us how to do encryption and decryption using RSA. What we will do is that we will now take an example. So, you might still be wondering that this is still pretty difficult, and we took one example where things are very easy and so on. So, as I mentioned in our last lecture is that most of the programming environments will support some form of functions that you can use, library functions, which you can use for actually generating public key and private key pairs. You do not have to do all those steps yourself. And then what we will do now is that we will see that there is a tool that can be actually used for generating this public key private key pair. So, you can see that here is this particular site. As I clicked and reached this particular site, and then it is very simple that you can select what is the key size, which is chosen here as a 1024 bit, and that I simply click on generate RSA key pair, and you see that immediately we have got this public key private key. So, this pair is obtained. Okay. And then if we want to do encryption and decryption using this, what we have to do? We have to have a plain text. So, which we will first encrypt with the private key, we will first encrypt with the public key and then we will decrypt it with the private key. So, let us consider that there is a plain text and I say that plain text is hello world, okay. And then if we enter the public key. So, if you see here we have the public key generated. So, I am selecting that public key and I am saying that enter the public key or private key and I say it is the private key and I click on encrypt. So, what it has done is that it has encrypted it and generated the output, okay. And whatever output is generated. So, if you want to decrypt it, what you have to do is that you have to put it on the right hand side part of this web page. So, in effect what we have said is that let this public key and private key pair that was generated is that of Bob, and Bob's public key is known to everybody including Alice. So, Alice wanted to send this message hello world and Alice encrypted it with the public key of Bob and got this as the encrypted output. So, this in effect is our ciphertext, although it has been encoded into some particular form. And now what we do is that now we are sending as if this to Bob and Bob has received this as a ciphertext and now Bob will try to decrypt it. And what key Bob will use? Bob will use his private key. So, I am copying that private key here and then I am choosing that as the private key and I say decrypt, and you see that we get back hello world. So, that is exactly what will be done by Bob as Bob gets this ciphertext from Alice. So, that explains to you the basic concept of encryption and decryption using RSA and how the ciphertext can be converted back to plain text once it has been received by the intended recipient. So, that was an illustration for our understanding, and now what we will do is that now we have seen the application of RSA in converting a plain text into a ciphertext and sending it to the recipient, so that in between if an attacker also gets that ciphertext, because the attacker does not know the private key, will not be able to decrypt it. Now, let us see its application, that is application of public key cryptography in digital signature. Now, here it works just in the opposite manner. So, what is done is that here Alice first will encrypt the message with her private key. So, her private key. So, Alice is sending a message to Bob and it is going to put the digital signature, meaning as we have explained that Bob would be able to verify that indeed it was sent by Alice, and Alice also will later on not be able to deny that she had indeed sent the message. Okay. So, that is what we call as the digital signature, and for doing that what Alice will do, as is mentioned here, if you see that Alice will now sign the message. Sign means we can for the time being consider it is encrypting it with her private key, and then it is sent to Bob, and Bob will be able to verify this using the public key, but public key of Alice. Okay. So, in this process as such Bob's keys are of no use, just as in the previous example we did not talk anything about Alice's keys. So, everybody has Alice's public key. So, once Alice has signed a message with a private key, anybody including Bob would be able to check whether indeed it was sent by Alice. Okay. So, as we see here in this diagram that there is this message M that is being sent, along with that this is the digital signature that is also sent by Alice. And what is this M prime? M prime is encryption of the message M, which is same as this one, and it is encrypted with the private key of Alice. Okay. And then this is being sent along with the message, and now Bob receives M. So, Bob has got back the message from Alice, and mind it, so far we have not encrypted M. So, let us assume that it is not something which is confidential. If anybody else knows about it, there is no problem, but what Bob would like to know is that it was indeed sent by Alice. That is the requirement. Okay. So, what Bob will have to do is that Bob will have to ensure that it was Alice who must have sent this message. So, what can Bob do? Now, this is where this public key of Alice will be used. So, what Bob will do is that now Bob will verify the signature using Alice's public key. So, this m prime that was sent along with m, what Bob would do is that Bob would now, so I would say this should be written as decryption, not encryption. So, Bob will be using the public key of Alice in order to decrypt this m prime, okay. And then it will get back something, and if that something matches with this m, then what it proves? It proves that this m prime must have been encrypted with the private key of Alice, because it can be decrypted with the public key of Alice, and only any message that has been encrypted with private key of Alice can be decrypted with her public key. Hence, Bob knows that it must have indeed been sent by Alice. So, that is the whole purpose of digital signature. As we have discussed before, that it is like a signature that anyone can verify, and also Alice cannot later on deny. So, that is what has been achieved by using this digital signature using public key cryptography. Now, in this example, of course, that we have to encrypt this entire message with this private key of Alice, okay, and then we get m prime, and then it is to be decrypted, and all we want to ensure is that it must have been sent by Alice. That is all that needs to be done by using this concept of digital signature. And if that is the case, what also can be done is that instead of encrypting the entire message m using Alice's private key, what is done is that instead we first generate a message digest for signing instead of the original message. So, we have the original message m, from there we first get its digest hm. Now, this hm is actually encrypted using the private key of Alice, and that forms the signature S. And then what is done is that once Bob gets that, Bob will be now decrypting this S with the public key of Alice, and then whatever it is obtained after that process of decryption. Now, what Bob has to do is that now Bob has to apply the same hash on this message m, and then it has to check whether that is matching with what he got here by decryption of this S with the public key of Alice. So, let me summarize the steps. In effect, what will be done is that Alice will first generate the digest of the message, then Alice will encrypt that message digest with her private key. Now, Alice will send the message as well as this signature, which is the encryption of the digest with her private key. So, this m and s is what will be sent by Alice to Bob. Once Bob has received both the m and s, so Bob has got the message, but Bob has to verify that it was indeed sent by Alice. So, Bob will do what? Bob will apply the decryption process using Alice's public key on this s, and Bob will get something. Now, that something that Bob gets, does it match with the hash of the message that was sent? So, for that Bob will apply the same hash on m and check that what he gets here indeed matches with the hash of the m that he obtained. So, if these two are the same, then that means that it must have been sent by Alice. So, that is how we reduce the signature size by making use of the message digest. So, if you just go to the same concept once again, now you can see that here what we need to do is that now if we say again generate this public key private key pair, what we have to do is that we say generate again now public key private key pair, and if you see in this example, these are supposed to be the public key private key pair of Alice. Okay. And now, what you understand is that if Alice is want to send this same hello world, then what Alice will do is that Alice will first encrypt it with her private key. Okay. So, Alice is going to encrypt it with her private key, and then what it will do is that it will encrypt it, and the same one now will be sent to Bob. So, Bob gets this, and Bob will now use Alice's public key here, and then mention that it is a public key, and Alice and Bob will decrypt, and you see that again we are getting back hello world. So, what it means is that this was sent to Bob, which is the output, okay, and then this is what we see here. This was the output of the process that Alice had carried out, and Bob has received it, and Bob applies the decryption process using Alice's public key, and Bob sees that he gets back hello world, and this hello world will be matching with that message. So, it means that it indeed is something that was sent by Alice. Okay. So, that is how things work, and then what you could also do is that along with this process you can also apply that generation of the digest following this link that we had seen in our earlier classes, and you can now try the same steps that were mentioned here, and you will see that it will also work by sending the message digest instead of the digital signature applied on the complete message itself. So, if you remember that this is the link that you can use, and you can actually go to that link to first generate from this message hello world, you could first generate its digest and give the digest as input here as the text to encrypt. The rest of the steps would be similar, and then what you will do is that you will get back the digest, and then if you apply the same hash function on that message M, you will get back the digest and the two will match. So, I would leave that as something that you can try it out yourself. It is a very straightforward extension of what we have seen before in terms of generating message digests, and also what you can do by doing this process of encryption and decryption using private key and public key for generating the digital signatures. So, in a blockchain, now what is the use of a digital signature? It is used to validate the origin of a transaction. In blockchains, we will see that information is captured in the form of what we call as transactions. Okay. So, it prevents non-repudiation, meaning that Alice later on cannot deny her own transactions. That is what we have said is a property of or the reason why we want to make use of digital signatures in a blockchain, and also no one else can claim that Alice's transaction as his or her own transaction. So, if a transaction has been made by Alice, now some Carol cannot say that I made the transaction, because this digital signature cannot be validated using Carol's public key. And then there are many different types of algorithms for public key cryptography, and Bitcoin uses ECDSA, and there are many others. So, other different blockchains can use other types of cryptography, and this is based on what is called elliptic curve cryptography. It has got good randomness and key generation, which is very important, as we have said. Now, finally, if we consider the application of hash chain and digital signature, say Alice is generating 10 coins, say 10 bitcoins or something. So, Alice generates 10 bitcoins. So, that is a transaction for generating 10 bitcoins. We will later on see actually how these bitcoins are generated, and then along with that Alice also signs it with her digital signature. So, she uses her private key to sign it. So, this transaction of Alice generating 10 coins, so that is A:10, along with that we have the signature of Alice. Okay. Now, what happens is that, say the next transaction is that out of these 10 coins, Alice is paying 5 coins to Bob. So, if you see in the first block here, we have this one transaction which says that Alice has generated 10 coins and signed it with her digital signature, and in the second block we have a transaction. Let us assume for the time being every block has only one single transaction. So, here what Alice has done, Alice has transferred to Bob, we see A and then arrow to B, 5 of those coins, and then again Alice is signing that with her digital signature. So, it means what? Now, Alice has transferred out of 10, 5 to Bob. Okay. So, now that this transaction of transfer of 5 coins from Alice to Bob also has been signed using the digital signature of Alice, hence later on Alice cannot say, oh, I did not do the transfer. Okay. So, Alice cannot later on deny it. Similarly, nobody else like Carol cannot claim that Carol did the transfer to Bob of those 5 bitcoins, because this digital signature sig A can only be verified using the public key of Alice and not that of Carol. So, that is the basic concept of how digital signatures can be used in blockchains. So, overall, now to summarize what we have studied in this set of lectures, these 5 lectures which are in the area of basic cryptographic primitives required for blockchain, we have first of all understood what is meant by cryptographic hash functions, and also we have talked about digital signature. In today's lecture, we have shown how to encrypt and decrypt using public key cryptography and how this has application in digital signature and how digital signatures are indeed used in blockchains. So, our same set of references are there, the Cryptography and Network Security book by William Stallings, we took that example from this book, and also this book on blockchain basics, and there are several other such nice books on blockchain, which will give you these ideas about how digital signatures are used in blockchain. So, that brings us to the end of today's lecture. Thank you very much.